Hi, my name is Stijn and I'm part of the technical product management team covering NSX at VMware's Networking and Advanced Security Business Group. In this demo, I'll cover how NSXT 3.2 with the distributed IDPs and distributed firewall can detect and prevent attempts of exploiting CVE 2021-44228, also known as Log4Shell. Before I start, here's a quick disclaimer. There are many ways Log4j can be exploited, and this demo is just an example of how the NSX distributed IDPs can detect one of these ways. You should follow proper cybersecurity hygiene best practices to minimize your risk. For this demo, we have created an organization called GoFinance. They're hosting a number of applications in their data center. Some of these applications are intended for customers and are exposed to the outside world, while other applications are only exposed to employees on the internal network. A malicious actor discovered one of the public applications is vulnerable to the Log4Shell exploit and will attempt to use this to gain initial access into the GoFinance environment. This vulnerability is exploited by a malicious actor sending an attack pattern containing a JNDI or Java Naming and Directory Interface instruction with a particular protocol such as LDAP. To send this pattern, attackers can use the user agent of the HTTP header or use an HTTP form entry field. The vulnerable Log4j server will then make a query, for instance an LDAP query, to the server that the malicious actor specified in the JNDI pattern. The LDAP server then responds with directory information which contains a second payload link to a Java class that contains a malicious payload, which is then executed on the victim, after which the attacker can gain access to the system and move further within the network and deploy ransomware, crypto miners, or perform other post-exploit activity. In our example, we'll see that once the attacker has gained initial access, they use the same exploit to move laterally from the application deployed in production to an application deployed on the internal network. From here, without proper segmentation, the attacker could discover and move further within the environment. Once we've demonstrated the attack, I'll show how the distributed IDS can detect the initial exploit in the lateral movement, and then we'll have a look at how, through network-independent segmentation with the distributed firewall, we can prevent lateral movement, and how by changing our IDPs to prevent mode, we can block the initial exploit. I'll finally show how we can use the distributed firewall to prevent unneeded outbound communication. Here we're looking at the attacker screen. We're using the proof of concept I provided a link for earlier in the demo. This proof of concept comes with a Python script which sets up a fake LDAP server as well as an HTTP server. The attacker is also running Poundcat, which is a bind and reverse shell handler, which allows them to interact with the victim once it's been compromised. The script generates the JNDI string, which we can simply paste into a form on the vulnerable web application of our target, GoFinance. As soon as we do that and submit the form, it sends out the LDAP query and the Java class with the exploit payload is delivered. Immediately after that, a reverse shell is established from the vulnerable web server to my attacker's machine, and now I can interact with the server, which you can see is called app for web tier. Here you can see the IP address ends in 10.103. To discover the internal network, I'm installing nmap on this compromised server, and once installed, I'm using this to run a scan against a few networks. As you can see, we've discovered a number of servers also listening on port 8080, including one with an IP address ending in 10.107 and another one with IP ending in 10.100. Now I'm picking those to confirm that the compromised server can reach those internal IP addresses. Now I'll try to use the same exploit again against another potentially vulnerable server, the one with the IP address ending in 10.107. And this is an application deployed on the internal network. In this case, I used wget to send the JNDI string, and I spun up another fake LDAP server and an HTTP server for this vulnerable server to connect to. And as you can see on the right, now we have established another reverse shell, this time with a vulnerable server on the internal network called app5 web tier. I can also interact with this compromised server, and from here I could move further into the network. Now let's see what the NSX distributed IDs and IPs has detected. GoFinance has applied the distributed IDs and IPs in detection-only mode to the VNIC of every workload in their environment. Let's have a look at the configuration. Distributed IDs and IPs can be enabled for an entire vSphere cluster simply by changing this toggle. This does not require the installation of any additional components. Once enabled, NSX Manager will check the NSX Threat Intelligence Cloud for new IDPS signatures every 20 minutes and can automatically propagate those to all hosts. For every signature update, we can see what has been changed. Optionally, we can create one or more IDPS profiles, or we could just use the built-in default profile. Here we've created a profile that includes high and critical severity signatures, as well as signatures that indicate suspicious activity. Let's have a look at which signatures are enabled. And here we can filter based on things like CVE. Let me apply a filter based on CVE 2021-44228. And as you can see, at the time that I'm recording this demo, we have 95 signatures that cover various ways this vulnerability can be exploited, as well as various obfuscation methods that we've seen in the wild. These all ship with a default recommended action of reject, which means that we will drop these attempts if the IDs and IPs is deployed in Detect and Prevent mode. The final configuration step is to create a distributed IDs and IPs policy with one or more classification rules that specifies which IDs and IPs profile should be applied to which workloads. I've created two rules here, one for the public applications and one for the internal apps. I've applied the same IDPS profile to both, and these rules match traffic coming into the respective workloads, and the workloads are automatically mapped into one of these two groups based on a tag that is applied to each workload. You can also see that I have selected the Detect Only mode for both of these rules. Finally, although not part of this demo, I've also applied a distributed malware detection policy to these workloads. Now let's see what we have detected. The security overview has a number of dashboards that show what's going on in our environment. Specifically, the IDs and IPs dashboard shows that we've had a number of detection events, and we list high-level information about those, like the workloads with the highest number of detections. Switching over to the IDs and IPs threat detection view. Here we see all the events that were detected by the distributed IDs and IPs in our environment. These events are grouped based on signature, and for the purpose of this demo, we are interested in events related to Log4j, so we can apply a filter here. Now we see that one signature was triggered. When I open up the details and hide the timeline, we can see additional information about the exploit. There's also a link with details about the CVE. In addition, we map events to the relevant MITRE tactic and technique. You can see that two workloads have been affected by this exploit, the public app app4 web tier and the internal app app5 web tier. The intrusion history shows the details for every time the signature was triggered. Here you can see that the app4 web tier with the IP address ending in 10.103 was the initial target, and app5 web tier was the secondary target. You can also see that the app4 VM, which was initially compromised, was used as a pivot to attack the app5 VM. Now let's see how we can prevent lateral movement by segmenting the environment using the NSX Distributed Firewall. The Distributed Firewall is in essence a layer 2 to layer 7 stateful firewall that is transparently applied to the VNIC of every workload. This allows us to apply any level of segmentation without needing to make any network changes. We can, for example, group the workloads that make up each of our applications and create a bubble around each application, essentially isolating every application from every other application. By doing so, we can prevent lateral movement between the compromised public application and applications deployed on the internal network. Let's have a look at how this was configured. I've created a single rule for each of our 5 applications. The app1 rule specifies that workloads that belong to other apps cannot communicate with workloads that belong to the app1 group. This app1 group includes all the workloads that make up this multi-tier application, and workloads became a member of this group based on the app1 tag being applied to them. The remaining rules for the other 4 apps are built exactly the same. Now let me enable these rules. In addition, I've also created a DMZ access policy which specifies that external IP addresses can access the web tier of the public applications. Let me enable this rule as well and publish our changes, which immediately realizes this policy across the environment. Let's now run the exploit attempt again. We start again by copying the J and the I string into the username field of the vulnerable public app. As you can see, the initial access still succeeds and a reverse shell is established. That is expected as we don't have a policy in place to prevent this. However, Now, when we try to ping the internal app, you can see that this fails. Also, when we try to pivot the attack by running the exploit again against the internal app, as you see on the right of the screen, no second reverse shell gets established. Let's now prevent the initial exploit, and we can do that by changing the IDPS mode from Detect Only to Detect and Prevent. This will block the delivery of the HTTP parameters containing the J and the I string to the vulnerable public server, and would do the same if the attacker is already on the inside and attempts to use the same exploit against vulnerable internal servers. Making the change is really simple. We just go to our two IDPS rules and change the action from Detect Only to Detect and Prevent. Let's try the exploit again. Now you can see that the initial exploit fails, no reverse shell is established, and the connection is reset. The reason for the reset is that this signature ships with a default action of reject, which drops the flow and sends a reset to both sides of the connection. Let's have a look at our IDPS events and confirm this. You can see that now we have some green color on top of this bar. Green indicates that we took a preventative action. Clicking on the intrusion history confirms that we indeed rejected this intrusion attempt against the public application. Finally, let's have a look at how we can further increase our defenses by explicitly preventing our server workloads from initiating communication with the outside. In case of this exploit, this would prevent these workloads from reaching out to the attacker's LDAP or web servers. To accomplish this, I've added a policy with a single rule. This rule specifies that the internal and public applications cannot talk with anything on the outside of the organization's network. You can of course also add exemptions such as allow communication with update servers or GitHub based on FQDN filtering. Let me enable this policy and try the exploit one more time. And as you can see, the exploit attempt fails again. For more information about Log4Shell and how the VMware Security portfolio, including the NSX Distributed Firewall, the Distributed IDs and IPS, the Advanced Load Balancer, and Carbon Black can help you protect your environment, check out the VMware blogs that I've mentioned at the beginning of the demo.